Thank you very much for everyone for coming, and thanks for the invitation. Very happy to be here. I'll be talking about some recent work that we just put last month about symmetry, topological order, correspondence, and this framework, and getting this symTO data from low energy properties of some critical theory. Essentially, that's the sort of the goal. This work was done with Jesse, who is a now second-year PhD, with Sang-Hee Shu and Xiaogang Wen. So symmetry, topological order, also called symmetry, topological field theory, also sometimes called topological holography, is a very quickly growing field. There have been a lot of papers recently. This is the papers I collected until 2025. I didn't even put this last year, but essentially it's exploding. Yeah, I'll not cite all of these again. I just wanted to show that this framework has been very intensely studied, and people are trying to find new applications. I try to give a sort of, I use the word symTO, symmetry topological order. I'll try to give a very quick summary of it. So symTO is a theoretical framework where one tries to represent or simulate the properties of some d-dimensional system using a d plus one-dimensional topological field theory. So in this talk, I'll mostly focus on one-dimensional systems and the two-dimensional topological filters, or 1 plus 1 and 2 plus 1 dimensional. So the idea is that we start with some theory, this TC, that is a 1 plus 1 dimensional system with, in general, some generalized symmetry that is described by some fusion category C. And then we separate the dynamics of it from its sort of symmetry-related universal data by representing it as a 2 plus 1 dimensional topological field theory, whose bulk excitations or defects are described by what's called the Dirichlet center of this fusion category C. But the main idea is the following. So this two-dimensional topological field theory is gapped in the bulk. And then this is what's called the sandwich construction, where I'm thinking of some slab of this topological field theory. And then it has two boundaries. The top boundary, which I call B sim, is also gapped. And then B physical, I don't specify. So the construction is that since the bulk topological field theory is a topological field theory, its width or the length scale is not important. So I can freely actually squeeze it. And the idea is that once I take this top topological boundary and push it to the bottom, I should simulate or replicate back my physical system in 1 plus 1D, this TC. And the exact matching is that as the limit of the bulk gap and the top boundary gap goes to infinity, or below those gaps, the excitation spectrum of this topological field theory should replicate the excitation spectrum of my theory TC, or some sector of my theory TC. Therefore, the bottom boundary, which does not have to be gapped, it can be gapped or gapless, essentially encodes all the dynamical data about the energy spectrum or the excitations, or if it's gapless, maybe velocity, all the non-universal data. Whereas, as I will try to argue, the top boundary decides the universal data, namely it decides the symmetries, what are the symmetry defects, fluxes, and then what are the charged objects. Now, in 2 plus 1D, given some topological field theory, the gap boundary conditions are described by what are called the Lagrangian condensable algebras, which usually specified by some direct sum of anyons of the bulk theory, together with some multiplication rule. I'll only discuss some simple cases where just specifying what anyons are condensed would be enough to specify the Lagrangian condensable algebra. But these anyons should be condensable in the sense that they must be self-bosons. So they have trivial self-statistics, and they also have trivial mutual statistics, so you can simultaneously condense them. Then, as I said, we choose some top boundary that is gapped. There are some anyons that are not condensed at the top boundary. They'll form their own fusion category, the defects at the top boundary. which will essentially be the symmetry operators that can act on the bottom boundary. So that's how the top boundary can decide on what are the symmetries of this physical system. Now imagine that, as I said, we can choose anything for the physical boundary, but let's imagine that we choose some topological boundary for the bottom physical boundary as well. Then the entire system is gapped. Then this would allow one to actually classify different gap phases with symmetry C. So that's sort of one utility of this symTO construction. So it allows a classification of gapped phases with sort of generalized symmetry in 1 plus 1D. Just to give maybe the simplest incarnation of it is that let's take the Ising model in 1D. That's something that we all know. So depending on the couplings J and H, this is either in the disordered phase with unique ground state or in the ordered phase with ferromagnetic order. The corresponding two-dimensional topological field theory can be thought of as actually toric code, so the deconfined phase of ZT gauge theory. And toric code has two kind of gap boundary condition. One is what's called an E-condensed, the other one is the M-condensed boundary condition, because there are four kind of anyons. Apart from identity, E and M anyons are self-bosons, but their combination is a fermion, so you cannot condense them. So the only thing you can condense is identity together with T or identity together with M. Now let's imagine that we choose the E condensation for the top boundary. Now what is not condensed, essentially what is not determined by the top boundary is the M lines, because any E line can be pushed to the top and absorbed to the top, so they are trivialized sort of. And not trivialized M lines act like symmetry operators when squeezed to the bottom. Now I can also choose two gap boundaries for the bottom physical boundary, again with the same choices, E and M. Now since I declare that the M anyons are, like my M lines are symmetry operators, the charged object under this symmetry would be the E anyons. So when I condense the E anyons at the bottom, I'm sort of condensing a Z2 charge, and the ground state must be breaking the Z2 symmetry spontaneously. So this describes the ground state degeneracy is twofold, and this describes an SSB phase of this Ising Z2 symmetry. So that's the ferromagnetic phase. Now, as opposed to that, I can choose the M condensed boundary at the bottom. Now I'm sort of condensing the Z2 flux because I declared M line to be my symmetry operator, and an M anyon appears at the if I have an open M line, the M anyon appears at the end of the line, and then that would be like a symmetry flux essentially. And if I choose the bottom boundary to be also M condensed, this is like Z2 flux condensation. So that's the disordered phase, which is the paramagnet with unique ground state. Now notice that the toric code itself has some internal symmetry where you can exchange the anyon labels E and M, and the toric code doesn't change. This EM exchange symmetry, if you apply to the top boundary, essentially changes E condensation to M condensation, but it also changes the phases, because now what you call charge becomes flux and what you call flux becomes charge. Therefore, it applies, it essentially acts like Kramer-Venner's duality symmetry. So that's sort of my very quick lightning symTO example. But what I want to do is I actually want to construct some symTO given some gapless theory. So that's what I'll focus on, and I'm hoping that what I have described so far will help you to follow. So we've been trying to understand the excitations in a gapless system in terms of some anyon data of the one higher dimensional theory. And we wanted to sort of benchmark our understanding by taking something that we all know, or something that's very well known, namely the Spin-1/2 antiferromagnetic Heisenberg model, where the Hamiltonian is just nearest neighbor Heisenberg coupling between spin-1/2 degrees of freedom. This Hamiltonian has two symmetries. First, it has a faithfully represented continuous SO3 spin rotation symmetry, and it has the translation symmetry on the lattice, which is a ZL group. There is actually a constraint, because of these symmetries, there's a constraint on the ground state of this Hamiltonian, what's called an LSM theorem. Namely, since each translation unit cell supports a single spin 1/2 degree of freedom, which realizes a projective representation of the SO3 spin rotation symmetry, Edison theorem tells us that the ground state cannot be simultaneously non-degenerate, gapped, and symmetric under both symmetries. And indeed, this Hamiltonian has a gapless spectrum. So the ground state is symmetric, but it's also gapless. Actually, I will not even focus on the entire SO3 spin rotation symmetry. I'll only focus on some subgroup. The abelian Z2 times Z2 subgroup of SO3 spin rotation, which is realized by just pi rotations around X, Y, and Z axis. It turns out that to get the LSM ingapability constraint, you don't need the full continuous symmetry group. Instead, you can just focus on this discrete subgroup. And the interpretation is that this discrete subgroup participates in a mixed anomaly with the translation symmetry, which is realized as a just ordinary shift of the spin degrees of freedom.
So can I just ask about, so the goal is, your goal is to understand these gapless modes in terms of bulk data, but on the other hand, these gapless modes weren't forced by anything, right? Or it could have been gapped.
It could have been gapped at the cost of breaking some symmetry.
Right.
So I want two things actually. I want to both understand the excitations and the gapless theory in terms of some bulk topological order. I also want that bulk topological order to have access or capture of the nearby gapped phases, or tell me about something new about the nearby gapped phases once I do that. If I keep the full continuous symmetry, of course, that sort of forces me.
But your whole bulk business, it only cares about symmetries, right?
Yeah, that's
so it won't be able to distinguish possible scenarios, IR scenarios.
Oh, I see what you mean. Yeah, I think the bulk topological order applies to any system with that symmetry. That's true. That's true.
Question. So when you say it's enough, like how do the way you specify this particular subgroup is the smallest subgroup such that you still have this LSM?
Yeah, that's true. Yeah, I think you cannot take just one Z2. You need to both Z2s, and the way to see it is that once you look at each unit cell, the Z2 generators on each unit cell still anti-commute. They still realize projectively because a single sigma X and sigma Y or sigma Z anti-commute.
And is there something like, is the reason you take like the smallest one, like let's say I had some other discrete subgroup of SO3 that contains this, the bulk TO will be?
Bulk TO would be larger. It would also have more gapped boundaries. This is like a minimal incarnation, if you wish. That's true. I can always take a larger subgroup indeed. And then there will be more possibility.
I'm also a bit confused about the starting point. Why are we working on the lattice here? I mean, the symmetry TO picture is a continuum field theory picture. The gap has already been taken. The continuum limit has already been taken. So I'm not even sure it works for general lattice systems. Yeah, it certainly doesn't incorporate translation.
Actually, I'll get to the continuum because then I'll actually try to derive the emanant symmetry group of this lattice model by focusing on the just low energy degrees of freedom. The reason why that is the case is that we actually wanted to do this with just ED data. Of course, we don't need to do ED here. You know exactly what the continuum theory is. But more generally, you should think of this as more like a benchmarking project. And then more generally, you may want to have a lattice model where you don't know much about it. And you want to just use some numerical method and then obtain maybe some information about the symTO that corresponds to it at low energies. Yeah, you'll maybe see very quickly because my next slide. Oh no, not the next. Okay, the next slides will be just continuum theory. Actually, yeah. I'm just trying to now showcase the application of LSM theorem just to show what is known about the nearby phases. So this critical point is very well known. We can think of some perturbations of this type where delta A is some measure of anisotropy. So A is X, Y, Z. So it tells you how much you deviate from the Heisenberg model. And the J is the next nearest neighbor coupling, essentially. These perturbations preserve only that particular subgroup that I wanted to choose, namely Z2X times Z2Z internal symmetry and translation. And according to LSM theorem, there's a sort of what's called an LSM anomaly that forbids an undergenerate gap ground state. And indeed, if you perturb this critical point, which is labeled by this dark black lines here. Actually, this entire line is the same criticality, I think, but by these perturbations, you only open a gap at the cost of breaking one of the discrete symmetries, namely the 3 nil phases. If you tune the J to 0 and just turn on the anisotropy, you derive the system to one of the nil phases. So because when you add on anisotropy, you essentially make the system more Ising-like. They break always the internal symmetry group down to some Z2, together with breaking the translation. So here I implicitly assume that the lattice system size is even, so the translation is also broken by one side. Then the next nearest neighbor coupling, what it does is that when it is sufficiently large, it opens a dimer phase, which actually preserves the internal symmetry, but it breaks the translation symmetry only by one lattice side.
So the black dot point actually has the full SO3 symmetry.
Yeah.
So what happens to that? What's the pattern of breaking of that symmetry?
You explicitly break it by adding these perturbations. There's no SO3 anymore once you add them. Except J. If you just tune J by choosing delta A to be 1, you are in this line. That's why I said that actually the entire line has the SO3 symmetry still. What J flows to is some marginally irrelevant operator. Except this point at some J critical, it becomes exactly marginal. And after that, it becomes marginally relevant and opens a gap. Yeah. Okay, so we know this theory, the low energy theory that is described in this critical point. It's actually something very well known. It's the C=1 compact boson CFT at the self-dual radius. So at this radius, it also has an emergent SO4 symmetry, which can be written as SU2 times SU2 with some Z2 coset. And this is also what's known as SU2 level 1, as we know written theory. So that's just to say that we started with lattice model with SO3 and translation symmetry, but actually the continuum theory, of course, has more symmetry. It has the conformal symmetry as well. Now the goal is to somehow construct the symTO that captures or partially captures the symmetries of the low energy theory, which has this full SO4 symmetry. We will not be able to get the full SO4 because I will not even start with full SO3. I'll start with some discrete subgroup, but I'm going to show you that I will be able to capture some what I will define as emanant symmetry plus some signature of this emergent SO4 from the symTO data. And the strategy would be that I actually want to just use numerics. This model is integrable if you don't add J. If you tune J to be something else than 0, then you lose the integrability, but you can still do numerics. So I'll use ED. And the way I'm going to extract the symTO data will be the following. I'll think of the ED spectrum with periodic boundary conditions, where the low-lying excitations should somehow be representations of my symmetries. So they would be what I call charged excitations. They should be organized into the representations of my symmetry group, which is some Z2 times Z2, and maybe translation. Then I'll impose some twisted boundary conditions. In principle, only imposing Z2Z twisted boundary condition is enough because the others can be obtained by permutation. That's going to give me something about the fluxes. Essentially, twisting by Z2Z puts a Z2Z flux in the ground state, as well as some dions by looking at the excitations. Then I'll also look at periodic boundary conditions with some odd number of sites. I'll motivate why that is so. It turns out that the ED spectrum of this lattice Hamiltonian has some fourfold periodicity with the system size. And then you'll see why that it appears. And then there's a difference between even an odd number of unit cells. And then that I will interpret as the flux of some emanant Z2T symmetry. Okay, let me just first show the data with even L. and then try to motivate why there's this eminent Z to T symmetry. Now, this is just the ED data with 20 sites and up to some energy cut of 5. Now we notice that there are 2 towers of excitations, 2 cones of excitations, one localized at 0, the other one is localized around pi. And somehow this suggests that maybe the translation is acting like an internal Z2 symmetry on the low energy degrees of freedom, because I have 2 cones and the one cone realizes e to the ik1, the other one realizes e to the ik minus 1, sort of. So that I want to somehow interpret this as the states that carry some internal Z2 charge. And this internal Z2 comes purely from translations, because really the charge is determined by the lattice momentum. And that's what I want to call an eminent symmetry. There should be a reference. Okay, this has been recently defined. An eminent symmetry is, as opposed to an emergent symmetry, is exact even at low energy degrees of freedom, which means that there is no irrelevant operator that breaks this eminent symmetry, because it's coming from an exact UV lattice symmetry, which is the translation in this case. Whereas an emergent symmetry would be always broken, even at low energies. So that's an exact symmetry of this low energy degree of freedom. And I want to say that at continuum, this Hamiltonian has a low energy theory that has this eminent symmetry that is Z2x times Z2z, which are the exact lattice symmetries. And then there's the Z2t, which comes from translation. I essentially coset by translation by 2 sides. And the translation by one side sort of act like this internal Z2 symmetry.
If we restore the SO3 symmetry and the WZW description, can you tell me what Z2t is?
I think it is one of the, actually there's this emergent SO4. I think it acts as one of the Z2s in the SU2 left or right. Probably
like the center of one of them?
Yeah, center of one of them. I think there's a choice depending on, yeah.
The centers are identified, so.
Yeah. Okay, here is my reference for defining the eminent symmetry. Now, let's look at the odd lattice system size. Now, what happens is that, first of all, now I have odd number of spin 1/2 degrees of freedom. So my total spin number in the lattice has to be some half-odd integer. This means that every state has to be at least 2-fold degenerate, because I have some either total spin 1/2 or 3/2, whatever representation. That means that, yeah, every state is at least 2-fold degenerate. Not focusing on SO3 or SU2 representations, but just focusing on the lattice symmetries. It is because the 2 discrete symmetry generators for Z2Z and Z2X are now anti-commuting whenever L is odd. That's why there's an exact 2-fold degeneracy. Now with odd number of lattice size, odd number of lattice sites, we notice that actually the momentum is also shifted by pi/2. And somehow I want to interpret the case of odd number of sites as inserting a Z2T eminent symmetry flux at low energies. The lattice intuition is a bit sketchy, but it comes from some algebra like this. So if I have T to the L symmetry, that is flowing to some internal symmetry at low energy degrees of freedom, T to the L plus 1 being identity means that T to the L is like T minus 1, which means that I sort of inserted a translation twist. But that's not very well defined on the lattice. The correct interpretation is that you have a low energy theory where translation by one lattice side acts like an internal symmetry. And whenever you have odd number of sides, we want to interpret this as a twist of this internal symmetry at the low energy degrees of freedom. So I want to somehow coset by translation by 2 sides and organize the entire spectra in terms of charges and fluxes. When I say charges, I mean the representations and fluxes of the remaining total symmetry group.
Can you just say what was special about odd versus even in that intuitive explanation? I didn't quite get it.
Nothing is special because this holds for any L, whether
that's why I'm confused.
I think I just want to somehow interpret inserting one side as inserting a translation defect.
But can I do that no matter what the
That is true. That is true. But I know that the translation by one side flows to this Emanant Z2 symmetry. Maybe I should have said it that way. Therefore, I want to put odd number of sides as inserting a Z2T flux into the system. Z2T defect. You are right. Adding a side, no matter what, whether if there's an emanant or not, can be thought of as inserting a translation defect. But in this case, at the low energies, it also means that I'm inserting the Z2T. And the fact that my low energy momenta is now centered around pi over 2 and minus pi over 2 will have a consequence because it reminds us this anomalous Z2 flux. Because now my momentum eigenvalue is sort of fractionalized. It is half of what it was before. Okay, now I want to, with that interpretation, I want to organize things into representations of this group.
Can I ask about, so what is the continuum theory that corresponds to? I'm a bit confused about this.
This is still the same continuum theory, but with twisted boundary conditions.
So these would be gaplet fields at momenta around 2 pi over a times a quarter. And, so those are actual. We can talk. I'm just confused why you can't have zero momentums, low energy states by taking your low energy degree of freedom are two gapless fields.
Yeah,
roughly, right?
Yeah.
At momenta around a quarter and 3/4, right? Yeah. What about a two-particle state that has 1/4 plus 3/4?
No, this is the full ED spectrum, not single particle.
That's right. Yeah, so I'm wondering where these two-particle states are, where I have one particle with quarter momentum, one particle with 3/4, so that I have total 0. I would expect low energy states at 0 as well.
I see. I see. No, I think they have high. They are there. They're just because I only have 21 sites. They don't appear, but this you should think of
it looks very gapped somehow at 0 momentum. But surprised how.
It's theoretic boundary conditions with a twist. So like the moding in the compact boson description, the moding is such that as you go around the circle, the minimum modes not 0. But the minimum momentum mode is not 0.
It's you're saying it's like 1 over L ish or
no, I'm saying because it's twisted boundary condition.
Yeah.
Like you cannot impose there is no like the lowest energy mode is shifted upward because as you go around, you have to have a kind of reflection or whatever Z2T ends up being, reflection in one of the SU2s.
I guess the question is, why if you take a low energy mode at a quarter and at minus a quarter, together the energy should be at most twice.
Yeah, if it's weakly coupled, which we believe, I think.
No, it's like some vertex operator, right? So there'll be some cross term in the square and compute the scaling dimension, right? It's like e to the I k x. If you add the k's, you compute the dimension, you square that k. There'll be some cross term in the dimension. If you add the momenta of the vertex operators, the energy does not add.
Yeah, you're saying there's a on the previous slide it wasn't a vertex operator around 0, right? It was just d phi.
Yeah, but now that's not allowed.
Yeah.
So the lowest energy thing is a vertex operator.
Yeah.
Okay.
Okay, let me try to actually label these states. Maybe that will answer your question. So now I want, as I said, I want to interpret the states that are centered around momentum 0 as carrying no Z2T charge, and the things that are centered around momentum pi as carrying minus 1 Z2T charge. That's roughly the game. Then the ground state is carries no charge. It is 0 momentum, and then it has +1 eigenvalue under both rotations around x and z. So that's what I call my identity anyon. It is nothing. Now, if I try to look at the states, actually the lowest energy state turned out to be, the next lowest energy state turned out to be the one that carries some momentum. But if I just want to identify some representations of the Z2 x times Z2Z internal symmetry, and those are here. they are centered around momentum 0. Therefore, they have Z2T charge 1. And then there are 3 of them, exactly. And then depending on their charge, actually this is some convention, there can be other conventions. I just labeled them as EX, EY, EZ, as the E anyons of the Z2 subgroups coming from Z2X and Z2Z. And if you want to consistently label them, there needs to be, EZ needs to carry both the charge of itself and the charge of the other guy.
Probably it would help everybody if you said what they were in the compact boson language.
There were some e to the I guess, vertex operator.
Right, but I'm just trying to get this counting of there's 3.
Oh, I see. Yeah. This is
So
I see what you mean. So this is spin 0.
Yeah.
And this is the next spin 0 plus spin 1. And then these are the spin 1 excitations around momentum 0. So that's why there are 3 of them. And then that's why they come as the quantum number 0, -1, 1. So that's the spin 1 excitation, if you wish. But I don't want to label them by their SO3 representations. Instead, I want to decompose them into their Z2X times Z2Z charges.
No, I understand, but if we turn off those perturbations, we could label them by their SO3.
Yeah, of course. Yes, that's right. That's what, yeah, absolutely. That's right. Now here there are 4 states. That is a SO3 representation 0 plus 1. And then they are all centered around momentum pi. So their Z2T charge is -1 or k is pi. And then further, these 4 states can be labeled by having no charge under the X and Z, and then having charge under X or Z. So I labeled them as either pure Z2T charge or Z2XT charge, the diagonal, or ZT charge or YT charge. This is nothing unexpected because I have a dimension 8 abelian group. There should be 8 representations, 1D representations, and these are just those representations. Now each state is non-degenerate, although they are degenerate in terms of these eigenvalues. As you said, with perturbations, I can just split them. They are not degenerate. So I want to associate a quantum dimension 1 to each state. There is no symmetry ensured, or at least by these symmetries ensured degeneracy. Now, furthermore, I want to insert attach a topological spin to each state, because each anyon in the bulk topological order will have some topological spin. And then I want to relate the topological spin of an anyon in the bulk topological order with the momentum eigenvalue of these states. Namely, I want to check if the momentum eigenvalue of these states are some integer multiple of 2 pi over L, which I call spin 0. Spin I define as something that is modulo 1. So as long as I have some momentum that is integer multiple of 2 pi over L, I'll always call the corresponding anyons having topological spin 0. You will see shortly that there will be a case where we will deviate from that. So these are just 8 bosons, self-bosons. They are the charges. They are like E anyons of the toric code of this more complicated.
Wait, sorry, make sure the degeneracies of these things are sort of accidental. Right?
Yeah, because I have full SO3 symmetry in my ED code, just like Clay said. But if I put the perturbations, I can shift them as I wish. Okay, now the odd case. I want to interpret it as inserting a Z2T flux. Now, actually, every eigenstate is at least twofold degenerate, but the degeneracy is because of this symmetry group. So I don't count them as accidental. And I don't look at the lowest states. They are both, I think in this case, 4-fold degenerate, but only the 2-fold degeneracy is guaranteed by the symmetry. And they are actually, okay, what happens is that since I have odd number of sides, I can no longer diagonalize these 2 symmetries simultaneously because they don't commute, which means that I need to attach a minimal dimensional representation to the projective representation of this group, which is 2. What I'm trying to say is that this is really a block. It's a 2-dimensional irrep of the projective representation of this group. You can really not decompose it. It's just a composite object. Therefore, I attach both of them quantum dimension 2. And then if I look at the momenta that they are localized, I notice that it's actually localized around 1/4 times, -1/4 times 2 pi over L and +1/4 times 2 pi over L. So actually they carry some non-trivial topological spin. And then I want to interpret these as some semi-on-like excitations with topological spin 1/4 and 3/4. Yeah.
Shouldn't they be centered around pi over 2 and 3 pi over 2? Seems like when L is very large, they're centered around 0 and pi.
A mistake. Oh, maybe I made a mistake when I was writing this. Yes.
So the 0 and pi should be pi over.
Yeah,
2.
there's a shift. Yes, I think you are right. Pi over 2 and 3 pi over 2. Yeah, that's true. Exactly.
Several times when you've discussed the degeneracy, you said the phrase quantum dimension. Could you justify that identification?
No, not yet. I want to somehow, so the bulk topological anyons can have quantum dimension larger than 1, as we know, if the bulk topological order is non-abelian. Somehow I want to find a signature or something in the one-dimensional ED spectrum that simulates that, because there should be, the intuition is the following. Imagine that you have a symmetry operator or some bulk anyon line that is two-dimensional, and you try to put that anyon at the bottom boundary. That means that your low energy spectrum must be at least twofold degenerate, because there's some internal degree of freedom. And then now I want to interpret this two-dimensional degeneracy as literally putting that anyon at the bottom. And then that's why I call this quantum dimension. I just mean that the dimensionality of the representation.
But what if the bulk topological order had anyons whose quantum dimension was not an integer?
That's a great question.
What would you have planned for that?
The strategy is the following. I didn't want to tell about that, maybe in the outlook, but indeed, exactly, because this dimension can only be integer, and you can have some non-integer bulk anyon. I think you need to look at some scaling property. You need to insert many fluxes, and then look at the scaling of the quantum dimension. Sorry, scaling of the
degeneracy.
Exactly, as the number of, and then that should hopefully approach to some irrational. I know that for Kramer-Werners defect, it goes to square root 2, indeed, but yeah, here I only put one defect, so yeah. Okay, now I looked at the periodic boundary condition with even number of sites, odd number of sites. Now I want to put some twisted boundary condition by Z to Z. I just choose one of the internal symmetries. As I said, I can permute the label. That just means that when I have my spin operators and I take them around the chain, I'll just have a minus sign on the X and Y. But importantly, the translation operator no longer commutes with such a twisted Hamiltonian, so I need to modify my translation operator as well. So now there is a twisted translation symmetry, TZ, which is the old translation times just the local representation of this spin rotation symmetry. The property of it is that when you translate by L sites, of course, you are conjugating by your global symmetry operator, so T to the L is no longer 1, instead it is RZ, and the T to the 2L is now identity. So now when I do the ED, I'll use a quantum number that's a quasi-momentum number that is 2 pi over 2L. And now my total lattice symmetry group also changes. It is no longer Z2X times Z2Z times Z2L. Instead, it is Z2X times Z2LZT, whose generator is this twisted translation. And importantly, once I insert a twisted boundary condition by Z to Z, now this twisted translation operator don't commute with my global rotation around X. The reason is that translation commutes with the global rotation around X, but then this factor picks up a minus sign, because it's, even though I exponentiated it once you put the spin 1/2 operator, this is just sigma Z. All right. Now I look at my, that also means that I cannot diagonalize both the momentum number and the Z2X quantum number. So I'll just diagonalize my momentum, and then I'll allow Z2X to act on it. So relate two different momenta. Namely, what I mean by that is that here, this is the, what I call KZ, twisted momentum. But then the states at 0 and states at pi are mapped to each other by the Rx symmetry operator. So they are sort of degenerate. What should one do ideally is that one should fold the Brillouin zone so that these states actually fall on top of each other and then become really degenerate. Okay, and then I look at two cases. One is even number of sites, the other is odd number of sites. The difference is that even number of sites means that I just insert the flux of Z to Z. So the low energy degrees of freedom are labeled by only the M anyons corresponding symmetry fluxes of Z. And the first excited states are labeled by the what I call FC. FC is a dion. It's a bound state of a Z2 charge, Z2Z charge together with a Z2Z flux, because those are only the quantum numbers that I can simultaneously diagonalize. And Z2X is just mapping things to each other. So it gives a twofold degeneracy. So both of these anyons are, or both of these states have quantum dimension 2 because there is an exact degeneracy from the Z2X symmetry. And then they are localized around 0 or pi over 2 modulo pi. So I associate with M anyons the topological spin 0. Now, if you look at the dions, it turns out that actually they are their momentum is localized around 1/2 times some multiple of 2 pi L. So I associate topological spin 1/2 to these. So that's why they are labeled by F. They are like fermions of the torico. They have topological spin 1/2. And similarly, if I look at the odd number of sites, the only difference is now that I inserted both a Z2Z flux and a Z2T, this eminent symmetry flux. But the labeling is similar. So now I have an M anyon of ZT and then this dion of, again, ZT with a ZT charge. And similarly, yeah, these two are mapped to each other under the action Z2X. Okay, so with that, if I also permute the label X, Y, and Z, I collect actually 22 states at the very low energies, like the ground state and the first excited states, first 1 or 2 excited states. And the first 8, I have already shown you. They were all quantum dimension 1 and topological spin 0. Those are the my charges, so to say. And everything else was a flux because I obtained them by either having odd number of sites or inserting some symmetry defect. And these ones that are labeled by M, they had topological spin 0. But then the rest have some non-trivial topological spin, so they have some self-statistics, either fermionic or semionic. Now it turns out that if you take just these collection of S and D, topological spin and quantum dimension, it matches exactly the topological order, what's called the D8 quantum double. Therefore, my claim is that the eminent symmetries of the Heisenberg antiferromagnet is captured by the D8 quantum double as a symTO. Now I'll further justify why that is so. So let's just
supposed to be a picture in the continuum, or on the left is the lattice model. What is the?
Yeah, I think this. I want to say that this is the continuum limit of that lattice model. I don't really mean that it's the discrete lattice model, and I think there the matching would not be exactly, because this would not be a topological filter in that case, because you need to ensure translation. Yeah.
So here you explained how you did a numerical route.
Yeah.
Maybe related to Clay's earlier question. To what extent could you have gotten the same if you start with the field theory, with the Z2 times Z2 internal symmetry, and once you identified that the translation acts as the internal?
I think I would get the exact same answer. That's true. Yeah.
So then, is it you do it numerically to show how you would do it if you didn't know the field?
Yeah, that's right. Exactly. So the hope is to sort of apply this prescription to something we don't know.
Okay. Yeah. Thank you.
Yeah. But you're right. Actually, I didn't need to do any ED. I could have just take the field theory. Or the symmetry action already tells me pretty much everything. Just the lattice symmetries. But then something more, I'll get something a little bit more than what I have provided. So this D8 quantum double is an non-abelian topological order. It has 11 gapped boundary conditions, which I organized in this way. You will see why. Now, if I choose these as my top boundary, they impose the following symmetries. The first one, if I only condense at the top boundary the E anyons, gives me a Z2 times Z2 times Z2 symmetry. with a type 3 mixed anomaly. This is what I have initially called LSM anomaly. This is not something unknown, it was known. And indeed, this is our symmetry. I choose this basis particularly because the diagonal part, when you multiply all of them, is the Z2T, this emanant symmetry, which is anomalous. Then the next four, if you choose them as top boundary, it gives you some non-invertible rep D8 symmetry. And the last six of them just gives you D8 symmetry.
Oh, sorry. So like in the case of toric code and Ising, you know that if you condense different ions in a bulk, then the boundary theories are related by phase transitions. So here, how are these different gap boundaries?
These gap boundaries are also related by some duality, like Kramer-Venner's duality, but I think what you want to simultaneously diagonalize E and M anion in the toric code case. I didn't get that part.
Sorry, like I was just referring to your example earlier.
Yeah.
Like there, you know that you have like if you condense E versus condense M, you have different phases in.
Oh yeah. Here also the labeling of phases exactly changes. There is a permutation, but it's not always, because you see in the case of toric code, you were preserving the symmetry. Both E condensation or M condensation would give you a Z2 symmetry, whereas here different condensations gives you different symmetries. So it will just map some phase with this symmetry to some other phase with that symmetry, and the ground state degeneracy will be different. Everything will be different. One may be SVT, the other will. Yeah, it's just a permutation of phases at the end. But actually, this reveals that there is some duality, which is also known, which I also contributed in the past, that between systems with Z2 cube symmetry with type 3 mixed anomaly, or in the lattice case, if you have an LSM anomaly between translation and two Z2s, it is known that there is a gauging map or duality between that and some sort of D8 symmetry. In the case of LSM anomaly, this D8 is not realized internally, but it's realized as a dipole symmetry. So, that is not something that's surprising, because I already started with an LSM, some system with LSM anomaly. I know that there's a dual system, dual description in terms of some dipolar symmetry. So the D8 quantum double is.
So what is the duality?
The duality is that you gauge, if you gauge one of the non-anomalous subgroups, Z2 subgroups, you get D8 symmetry.
Why does it become a dipole symmetry?
I see. Now, if it was internal symmetry, you would just get D8. Now imagine that instead this is some translation symmetry.
Okay.
Yeah, exactly. So translation X on one symmetry generator by shifting.
So this is what you would get if you did it on the lattice. But
exactly.
If you did it in the continuum, it would be an internal D8.
Yeah, exactly. It would be an internal D8 symmetry. Exactly.
So here it's the translation shifts swaps the two.
It swaps, and in some bases it takes one symmetry operator. So if you translate your dipole symmetry operator, you need to get something like dipole times your monopole dagger. So it does something like that. If it is, it works also for Zn times Zn. So if this is some Zn dipole symmetry, you will get Zn dipole times your Zn monopole symmetry or uniform symmetry generator. So there is this duality between systems with LSM and systems with modulated symmetries. Okay, now I'll talk about some gapped phases. Now let's choose the boundary to be the boundary symmetry to be the top boundary to be the symmetry that I started with. So 3 Z2s. Then the 11 phases are the following. So the first one is when you break the entire discrete symmetry to nothing, so with 8-fold degenerate ground state. The next four are the ones that we have already seen. They break this symmetry to some subgroup, Z2 times Z2 subgroup, and then they correspond to either dimer or the 3 Néel phases. One way to see it is that this boundary condenses only the charge of the translation. So that means that it will only break the translation, whereas it will not break the internal symmetry. That's why the surviving symmetry group is the internal symmetry group, whereas everything else condenses not only the translation charge, but also some internal symmetry charge. So the symmetry group that survives is also breaking some internal symmetry. So those are the Néel phases. And the remaining 6 is some other gap phases where this symmetry group is broken down to some Z2 subgroup. Those are all 4-fold degenerate. But now what I want to discuss is the following. I don't want to show the list, but if you believe me, D8 quantum double, just like toric code, has some symmetry. And in this case, it is an S4 symmetry. If you look at all the automorphisms, all the permutations of labels, they form the group S4. This condensable algebra that I choose for Z2 cube is invariant under all of them. That means that under those automorphisms of this, this quantum double, the top boundary will never change. However, the bottom boundaries are exactly mapped to each other, and this is why I grouped them in that form. So these four are permuted into each other under the action of S4. These six as well, they form an orbit, and then the top boundary is invariant. Now, there is this description of the critical point in terms of SO4 nonlinear sigma model, because it can be realized as a multi-critical point between 3 Néel phases and 1 dimer phase. As I said already, the continuum theory has an emergent SO4. This S4 action on these gapped phases exactly matches the S4 subgroup of this SO4 nonlinear sigma model. Therefore, somehow, even though I only input this symmetry, which came from some SO3 and translation, somehow the symTO has a signature of the emergent S4, which was really emergent. It was not some exact lattice symmetry. But it does not have the full thing, of course. It only has some subgroup. Yeah.
So maybe two questions. So these phases, is there any claim that the symTO can make that the field theory can access them in the nearby phase diagram?
No. Actually, I don't believe that they are accessible nearby. Yeah,
Okay.
you need to tune, and then you need to maybe go through some gapped phase to get there.
Okay, but the statement is maybe as long as I stay in a field theory with the same eminent symmetry, then I can maybe access it, but I might have to leave the.
Yeah, I think actually we tried a bit. I think only these four are accessible.
Okay.
Everything else is you need to go through something. Yeah.
I see. Second question. So the emergent SO4, right? As you said, it's only like if you tune yet this phase diagram, right?
Yeah.
For example, you tune away from the SU2 point along the compact boson line.
Yeah, then you get U1 only. You don't get it.
Right, but how do we see that? Like, where did you use? I'd say most of your analysis about the Z2 times Z2 times Z2 symmetry would also apply along that line, no?
Yeah, that is. I see what you are saying.
You
Yeah, that's
get
the-
U1 times U1. Don't you get U1 times U1?
You get U1 times U1.
Yeah, you don't get this permutation.
Yeah. Let me think about. Maybe that would correspond to some partial condensation, because I actually don't know the answer to this, but my intuition is that the Heisenberg antiferromagnetic at that point is when you choose this top boundary and choose nothing condensed boundary at the bottom with some particular dynamics, so to say. Maybe that line corresponds to some partial condensation, not a Lagrangian condensable algebra, but you condense only some anyons so that you are still critical, but something is gapped. That would be my naive guess, but I don't know if this
So
is.
even though you're enforcing less symmetry, you're saying that TO is gonna fine tune the marginal parameter to be the high symmetry point?
Yeah. But to be honest, I don't know why. Yeah. Because you're right, exactly. This discrete symmetry group exists also there, but somehow SO3 symmetry only appears in the SO4 symmetry. Okay, so that sort of brings me to my conclusion. So what I had showcased is that I used ED and some numerical methods to compute the eminent symTO of spin 1/2 Heisenberg antiferromagnet that captures also the nearby phases. And then it carries some information about the emergent symmetries as well. So one hope would be that maybe as you include more larger and larger discrete subgroups of SO3, maybe you can get larger and larger subgroups of SO4 as well. Maybe that's one thing to check. Now, in this construction, I only actually used two data, quantum dimension and topological spin, but this is far from, you cannot really pinpoint a topological order or topological field theory by just these two data. You need many more additional data. For instance, F symbol or the full S matrix is not derived at all. So one future direction is that can we really compute the full data just from some computation in the exact diagonalizations? Yeah, with that, thank you for listening.
So I guess we could do the same thing sort of for just the Eisen model.
That's true.
And there, would you like, what would you say about the But like there, I guess you would say something that like the EM permutation of the Tor code, well, that you say that carries information about the.
Yeah, but that is not exactly emergent, right? It's an exact symmetry of the Ising model at that point.
But suppose like you didn't know.
Ah, I see. Yeah, I would say that this EM duality carries some information there.
Is in the same way that this S4 is presumably it's not exact for the this S4 permutation. It doesn't it doesn't map to something exact on the lattice model.
It does not, yeah. Because in the lattice model, there's no exact symmetry that relates the dimer phase, really.
Yeah.
The S3 subgroup of S4 is exact because it's coming from SO3. It's just permutation of the three XYZ. But then permutation of those with the dimer phase is not an exact symmetry of the lattice. So it's always emergent, even at the critical point. So it's a little different than that case. But indeed, in the Ising model, maybe I would say that the EM duality means that there is some more symmetry at that critical point.
I have another question. So is there some yeah, I guess related, is there something I can do to make it so that the bulk kind of has the like this S4 symmetry is kind of gauged in the bulk?
Yeah, you can. You can take this bulk topological order and gauge this automorphism group because it's symmetry enriching the topological order. I don't know what you would get, but yeah, you can definitely do that. It would just give you some new topological order.
But does it mean something for the lattice model? Or
I think you are really then restricting yourself to the lattice models where this S4 becomes an exact symmetry and not an emergent symmetry anymore. So it should be some more special point than that critical point.
wait, so if there are no more.
Sorry, just one quick question. Is there a concrete Hamiltonian realization of these additional phases?
I think I can write ground states, then I can probably write some simple Hamiltonians, but they would deviate a lot away from the critical points. Yeah, I can write it. Because I can write down some ground state that breaks exactly those symmetries.
Okay. Yeah, if there's no more questions, thank Omer again for his time.